In this section we will study LTE-UE operations. After completing this section, you will be able to describe the UE system acquisition procedure in LTE. Explain the random access procedure used by the UE. Explain nature of LTE services and different types of LTE bearers. Explain COA's policy management function in LTE. Walk through the LTE end-to-end packet data session setup. Let us discuss life of a UE. As the UE is power on, it looks for the LTE network, registers with the selected network and exchanges data with the network. Step 1. When the UE is powered on, it uses programmed information, or most recently used network information, to decide which frequency to use to start looking for an LTE network. After tuning its receiver to that frequency, UE searches for the LTE cell transmission on that frequency. Step 2. Once the UE finds LTE cell transmission, it starts listening to system information, which is broadcasted in that cell. During this time, the UE is in idle mode, where it just listens to the system. Step 3. After UE learns the LTE system information, it uses its system access parameters. UE tries to access the network, using random access channel. Since multiple UEs may try to access the network at the same time, using same uplink resources, collisions may occur. So access procedures are defined, to minimize, and resolve collisions. Step 4. UE now registers its presence with the network. The network authenticates the UE, and allocates an IP address. Finally, the network may allocate radio resources to the UE, to enable efficient user traffic exchange. Let us walk through each of this step in detail. When a UE is powered on, it will scan its pre-programmed frequency list to find the strongest frequency. Then it will go through the system acquisition procedure steps. The first step is synchronizing to the downlink transmission of a cell. There are two parts of downlink synchronization. 1. Synchronizing to the slot timing of 0.5 milliseconds, and then 2. Determining where the frame begins. Once downlink synchronization is complete, the UE will be able to read downlink data from the cell. Particularly important are the system information broadcasts, which give the UE important information about the cell and the network. The UE will use the information in the system information blocks, SIBs, to determine if this is a cell it can use. This is the cell selection step. If a UE passes this step, it can go on to complete uplink synchronization, otherwise it must find another cell. Uplink synchronization involves the UE sending a signal on the PRACH. When the signal is heard by the ENB will respond to the UE with timing alignment information. Only after completing uplink synchronization will the UE be allowed to send anything else in the uplink, including the signaling required to create an RRC connection. An RRC connection is required for the UE to send the required NAS signaling for registering with the LTE EPC and subsequently establishing connectivity with a PDN. Each LTE frame consists of 20 slots. Each time slot contains 6 or 7 OFDMA symbols depending on the cyclic prefix used. Normal cyclic prefix contains 7 OFDMA symbols and extended cyclic prefix contains 6 symbols. In this example, we assume the use of normal cyclic prefix, CP. LTE defines two physical layer reference signals to help us achieve time synchronization with the network. Both primary and secondary synchronization signals are transmitted on time slots 0 and 10 of every frame. Synchronization signals are transmitted only on the center of 1.4 MHz of the radio channel independent of the channel bandwidth. The primary synchronization signal is always transmitted on the last OFDMA symbol duration of the time slot. The primary synchronization signal in each cell transmits one of three possible orthogonal sequences. The entire sequence is repeated in each time slot, and that helps the UI achieve slot-level synchronization with the network. The secondary synchronization signal is always transmitted on the second to last OFDMA symbol of time slots 0 and 10 of each frame. The secondary synchronization signal is made up of two binary sequences. When the UE acquires these two sequences, it can reliably derive the start and end of 10 milliseconds frame, that is, the UE achieves frame synchronization with the help of secondary synchronization signals. LTE systems use one of 168 possible sequences on the secondary synchronization signal. There are 504 possible combinations using three different sequences in primary sync signal and 168 possible sequences in secondary sync signal. This allows UE to uniquely identify a cell in a given area. System information is broadcast periodically in the downlink. System information is divided into master information block and a number of system information blocks. These information blocks convey information about various aspects of the radio channel and the network. The PBCH carries the master information block, MIB. System information block type 1, and all system information messages, are transmitted on DLSCH. The MIB contains critical information the UE needs before it can proceed. Once the MIB has been processed, the UE must then look for SIBs type 1 and 2, which provide configuration information and other parameters for the radio channel and the network. If for any reason, the UE is unable to read the MIB and SIBs 1 and 2, it will have to find another cell. Once the UE has the required information from SIB type 2, it is ready to begin uplink synchronization with the LTE cell. When ready to synchronize, the UE randomly selects one of the preambles from the pool it was given, determines its required uplink transmit power, and transmits the preamble on the PRACH. Not unlike other technologies, the UE will estimate its initial uplink transmit power based upon the received signal strength of the cell. After transmitting the preamble, the UE will begin to look for a random access response message from the ENB. If no response is received, the UE will try again at an increased power level for a finite number of attempts. The random access response from the ENB will contain a timing adjustment, a CRNTI, to be used as the ID for the RRC connection, and again for the UE to write its first uplink message, in this case an RRC connection request. The first message from the UE is the RRC connection request. The UE will include in this message its UE identity, and the establishment cause, for example, emergency, mobile-originated signaling, or mobile-originated data. The ENB responds to the UE with the RRC connection set up. His message is used to establish SRB1, and the UE will now be identified by a CRNTI which is assigned by the ENB. The details of SRB1 are provided to the UE by the ENB in this message. Finally, using the just allocated SRB1, the UE now sends an RRC connection setup complete message to the ENB to confirm the successful completion of an RRC connection establishment. It includes the selected PLMN identity from the PLMN identity list provided in the ESRB Type 1. On the successful completion of the RRC connection establishment procedure, the UE is in the RRC connected mode. Once system acquisition is complete and an RRC connection has been established, the UE will have to be registered with an MME in the EPC. In LTE, attaches the registration procedure that is followed. Once the UE sends an attach request, the ENB will select an MME to serve the mobile and the initial attach request will be sent to the MME. The MME, before agreeing to register the mobile, must make sure it is a valid user subscription and establish security with the UE. In LTE, the MME will manage authentication between the HSS and the SIM card in the UE. This will happen via mutual authentication such that the network authenticates the subscriber, and the subscriber, SIM, authenticates the network. If authentication passes, security will be established for NAS signaling, RRC signaling, and user traffic. Once attached at the MME will begin processing the PDN connectivity request from the UE. To do so, the MME will select a PGW and a SGW and will initiate the signaling needed to create a bearer path all the way from the UE to the PGW. This bearer, referred to as a default bearer, will remain established until the UE is detached and provides always-on connectivity for the UE to the selected PDN. It is during the establishment of the default bearer that the PGW can assign an IP address for the UE. In a typical case, multiple applications may be running in the UE at any time, each one having different quality of service or COS requirements. For example, a subscriber may use the web browser on their smartphone to browse to a website using a URL. The user pauses to read the website, and after a certain amount of time clicks on a link to an interesting blog article. While reading the article, the console user downloads an embedded YouTube video and watches a video clip for 1 minute. Once the video is finished, she might call a friend to discuss the blog and video they just watched. These applications require quality of service support from the network. For example, VoIP is constant data rate, low latency application. Web browsing on the other hand is bursty in nature but can tolerate delays better than VoIP applications. Streaming is somewhere in between. It needs higher data rates and low latency but can tolerate errors to a certain extent. In order to support multiple COS requirements, different bearers are set up within the evolved package system, each being associated with a COS. In LTE systems, an end-to-end bearer is defined using two components. First is Enhanced Packet System or EPS bearer, which is defined between the UE and the PDN gateway. Second is the external bearer, which is defined between the PDN gateway and the external application server such as web server. LTE doesn't control the external bearer setup. IP-based COS mechanisms including service-level agreements or SLA will be used to set up COS on the external bearer. For each application, an EPS bearer and an external bearer will be constructed. An EPS bearer identity uniquely identifies an EPS bearer for one UE accessing via eLEarning. The EPS bearer identity is allocated by the MME and is the one that carries the information. Usually it carries the user data. EPS bearers, which are a collection of radio bearers, S1 bearers, and S5 S8 bearers. Radio bearer. A radio bearer transports the packets of an EPS bearer between the UE and an E node B. S1 bearer. An S1 bearer transports the packets of an EPS bearer between an E node B and a SGW. S5 S8 bearer. An S5 S8 bearer transports the packets of an EPS bearer between the SGW and the PDN-GW. There is a one-to-one mapping between radio, S1 and S5 S8 bearers. This end-to-end EPS bearer realizes the negotiated COAs for the service. Broadly, bearers can be classified into two categories based on the nature of the COAs they provide: guaranteed bitrate or GBR, and non-guaranteed bitrate or non-GBR. GBR bearers will have associated guaranteed bitrate or GBR and maximum bitrate or MBR. Non-GBR bearers will have associated aggregate maximum bitrates or MBR for both the UE and the PDN. When GBR bearers are established, the ENB must make sure it has the scheduling capacity to support the bearer. This is achieved by admission control. Additionally, if the bearer is established, the ENB will reserve scheduling resources necessary to support the guaranteed bit rate. Non-GBR bearers may require admission control, depending upon vendor implementation, but will not cause the reservation of scheduler bandwidth. Since default bearers are established for all UEs in a network, it is required that the default bearer be non-GBR. As we delve into our discussion of bearers and COAs, it is important to clarify that COAs is defined for services, for example, internet, email, voice, etc. Bearers in the LTE network are established to support these services. LTE uses bearers to manage COAs. If we establish a default bearer for internet and want to add email service, we could add it to the same default bearer as long as the COAs requirements were the same. On the other hand, if we have a service like voice with different COAs requirements, we will establish a dedicated bearer to support the voice service. When a service is defined, COAs is established for that service. The COAs attributes of a service are associated with the LTE COAs class identifiers, QCIs. Services with QCI of 1 to 4 will require a GBR bearer and services with QCI of 5 to 9 will require a non-GBR bearer. Since we know that default bearers are by definition non-GBR, they will have a QCI of 5 to 9. Dedicated bearers may be established, as needed for any QCI. In addition to the bearer type, each of the QCIs have attributes relating to packet delay, packet loss, and priority. Priority will be used by nodes in the LTE network to prioritize IP traffic. This allows real-time types of services, like conversational void packets, to get through even if there is blocking on lower priority packets like FTP. Packet delay can be used by the scheduler in the ENB to determine when to deliver packets for the service. This delay is defined as the maximum time allowed for packet delivery from the PGW to the UE. Packet lost from the PGW to the ENB is assumed to be zero in non-congestion situations. Therefore, The packet loss in the table refers to non-congestion-related losses over the air. It is used by the ENB to determine how to set up features like automatic repeat request, ARQ, and adaptive modulation. Policy management plays a role to implement COS. Policy management is the process of applying operator-defined rules for resource allocation and network use. Policy enforcement involves service data flow detection and applies COS rules to individual service data flows. Multiple nodes in the EPC and LTE access play a role in implementing COS and policy management. The PCRF is the policy server in the EPC. The PCRF takes the available network information and operator-configured policies to create service session-level policy decisions. The decisions, known as policy control and charging or PCC rules, are forwarded to the Policy and Charging Enforcement Function or PCEF located in the PDNGW. The PCEF enforces policy decisions by establishing bearers, mapping service data flows to bearers, and performing traffic policing and shaping. The PDNGW maps bearers to the underlying transport network. The eNode B performs uplink and downlink rate policing, as well as RF radio resource scheduling. The eNode B, like the PDNGW, maps bearer traffic to the underlying IP transport network. The UE also plays a role in policy. In the uplink direction, it performs the initial mapping of service data flows to bearers. When the user wants to start a service that has a COS which is not supported by the default bearer, a new dedicated bearer can be established to support the COS. Here, the UE is sending application-level signaling, like Session Initiation Protocol, SIP, to start a new service. This might be the case if the operator has established an IP Multimedia Subsystem, IMS, services network to support features like VoIP or real-time streaming video. A COS policy decision is sent to the PGW and the PGW will apply the COS policy to the new dedicated bearer to support the service. At this point, the new dedicated bearer will be created. From an LTE air interface perspective, this is achieved in much the same way as the default bearer. Keep in mind, however, that if the new dedicated bearer is GBR, the ENB will have to apply admission control and reserve scheduler resources to support the minimum bit rate for the bearer. It should be noted that while this example is a network-initiated addition of a dedicated bearer, the UE can also initiate the addition of dedicated bearers via NAS signaling to the MME. This completes the module. Click next topic from navigation menu.